Okay, today we're going to try a different mode of communication. I'm going to use a whiteboard and short lectures on the whiteboard. So the topic today is angular momentum. And rather than have a very general discussion on angular momentum, we're going to focus on what happens to angular momentum when the particles are moving in circles. Maybe we start one particle, two particles, and things like that. And we'll get a couple of different ways we can write and think about angular momentum at the end of this. Okay? So here's a particle that's moving in a circle. Okay? Clearly, if let's look at the particle from this motion from a perspective of a couple of different perspectives, right? So, particle has a mass m, and it's moving, and it's got some speed here v, and it's moving about this center O, and there is a radius you can assign to that circle. You also know that in certain amount of time, this is going to cover certain distance depending on v. Assuming v is the same, so over here it's going to go this much distance is v delta t. So if I look at a small interval of time, it's going to cover that much distance. And if I look at the angle it will cover, is related to that, is delta theta. If you look at delta theta, that will cover will be how much distance is that way divided by r, right? V delta t divided by r. So this is the s. That's the s, and this is also. If you divide out delta theta, but divide delta theta by delta t, you can get this v over r. And you can see that this is angular speed, which we write omega, that's equal to v over r. Or you can say v equals to r times omega. This is a question that you've seen before. We just wanted to remind you that we're going to use this later. So this is one thing about things moving in a circle. The speed with which the thing is moving and the angular speed of what's the subtended angle, they are related to each other. So similarly, if you look at the momentum of this thing, momentum will give you how things are moving and what the mass is that's moving, right? So if I want to relate this to the angle it's subtended over there, that's when we discuss angular momentum. So let's look at it. So angular momentum. Let's look at the formula. I'll just give you the formula first, and then we will talk about it. The momentum of this will be magnitude-wise. Momentum is a vector, so we just look in magnitude. P equals to m times v. Angular momentum is also a vector, and so angular momentum, I'm just going to define it like this. I'm not showing you how it comes. Angular momentum, it's also a vector. So magnitude, we are going to use a letter L for it. L will be equal to, in this case it will be m times v times r. It's going to be m times v times r. For a single particle going in here, that's not the fundamental definition. It's not mathematical definition. But when something is going in a circle, in this particular situation, angular momentum is this. Now if I were to try to convert that into angular quantity, then you will see that there is a analogy between momentum and angular momentum magnitude formulas, right? So let's look at Okay, I had a little trouble at this point in video. Let me get erase it clearly. Alright, so I was here and video kind of stopped. So we want angular momentum. I'll just say the angular momentum magnitude is mvr in this of a particle in a circle. But in a circle, you know that v is also r times omega. So we can actually write this thing so that I get an angular quantity in there, right? So I have m r times omega times r, and then we separate out the angular thing from the rest, and we notice that we can group these things together, and we have very much a good analogy with what happened in the momentum. So it's like where we had a v, we have omega. So this is the velocity and this is the angular velocity. But where we had m has been replaced with this combination of things, right? This combination of things is playing the role of mass, that's the role of mass we're playing here. If you may remember that mass is actually another way to say about how much inertia is in the system, right? The higher the mass, the more the inertia. So this is an indicator of inertia of the system. And somehow this combination of things, mass with r squared, is playing a role of inertia in the angular system. In the angular quantity system, this becomes the inertia. And so instead of calling it a mass or something like that, we call this combination moment of inertia. Here, because we're just dealing with one single particle going in a circle, it's very simple. Take the mass and multiply it by the distance squared. The square of the circle, radius of the circle is going in. And we will denote this moment of inertia denote by letter I. We're going to do more inertia in another video. But right now you can see angular momentum has a magnitude which is L equals I times omega. And I happens to be, for this system, m times r squared. Even if you had more complicated system, you can always write L is I times omega. That's really much more powerful. Just like if you have much more complicated system, momentum will always be mass times v. Same as the case here. How about the direction? Well, you would like to keep track of which way it's going in circle. Is going this way or going the other way, right? So this is counterclockwise and this is clockwise. And so direction can be given two ways. I can say two ways. One is in a so-called clockwise, the sense of direction. So one is sense of rotation. So if is going this way, I'll call it angular momentum is counterclockwise. Going that way, I'm going to call it angular momentum is clockwise. So this will be clockwise or counterclockwise. Or counterclockwise. Okay. Another way to tell the direction is uses a right-hand rule. And right-hand rule works like this. I go from origin to where the particle is. So I go in the circle. I go from the center to where the particle is, and then I wrap my palm. So the bottom of my palm is along this line, and then I sweep in the direction of the velocity, and then the thumb points in the direction of angular momentum. This is very complicated. Another way to look at it, if you think of this circle has a plane in which the circle is. So in that plane is perpendicular to that plane is the direction, either perpendicular above or perpendicular below. So if this plane is in the board, then angular momentum will be either coming out, like in this case, this is coming out, or it's going to be going in. So this can be used, so-called right hand rule. One way to think about right hand rule is to just put this x and y axis here, and then we usually use right-handed coordinate system, which we use this way. So in this case, the z-axis is coming out. So how do I put z-axis? How do I draw z-axis here? Well, normally there's a convention of the arrow. So it's like a tip of the arrow coming at you. That's the z-axis. So in this situation, when you use right-hand rule, it's going to be either this coming out, or it's going to be, if you shoot an arrow from the back, so you're going to get an x of the arrow. So it's going to be this or this. So these are a couple of ways of doing angular momentum of a single particle in a circle. In the next video, I'm going to do angular momentum of a system which has more than one particle. So I'm going to stop here.